Good afternoon, everyone, and welcome to today's session on deep learning. Good afternoon, ma'am.
Good afternoon, Sakshi.
Ma'am, I have given you the rights so that we can start now.
Thank you. I will be starting.
Okay.
Is my screen visible?
Yes, ma'am, visible.
Okay, thank you, Sakshi. Yes, in today's class, we will discuss the next architecture, standard architecture, that is GoogleNet. So till now we have discussed two architectures, very important architecture. One is AlexNet, the other one is BGGNet, right? So let us see how GoogleNet or how many layers this GoogleNet has and how it is different from the other two type of architectures. Okay, first of all, the GoogleNet, this again is a winner of 2014 competition, that is ImageNet Large Scale Visual Recognition Challenge competition. Okay, and AlexNet was again it's been that particular architecture has won the first prize or winner in 2012 competition, and BGGNet that we discussed in the last class is runner-up of this 2014 competition. Okay, and let us discuss the details of this GoogleNet architecture. It has 22 layers. Again, if I count layers with the parameters, it has 22. If I also include pooling layer, then it becomes 27 layered architecture. Okay. It do have one special unit, I can say. It has 9 inception units. Again, in each inception unit, we do have set of convolutional and max pooling layer. Okay, we will see in detail about inception unit. Okay, because it has been added in this GoogleNet itself. We haven't discussed what is inception unit and what does it consists of. So we will discuss in today's class what does this inception unit comprises of. Correct? Inception module has 1x1 convolutions. It also has 3x3 convolutions. It does also have 5x5 convolutions, and it does also have some max pooling. Okay, and resultant of all these convolutions, okay, all these type of convolutions with different or variant of convolution filter size, I will be applying on the previous layer, that is the input image. Okay, I will be applying for the given input image, I will be applying 1x1 filter. I will also apply 3x3 filter. I will also apply 5x5, and I will also apply some max pooling on top on this particular given input image. The resultant output image will be output image that it will generate out of this particular operation. Output image generates on this particular operation. Output image, some output will be generated of this convolution operation, and some output will be generated out of this max pooling operation. Like this, we will be having 4 different output units. Okay, so those 4 different output units will be stacked one on each other. Okay, so that it will generate a single output volume. Okay, that means resultant of each of these operations whatever output that these operations are generating, I will stack all the operations together into single as a single output image, right? So this is how Inception module looks like, right? So Inception module with dimensionality reduction. So till now, like in AlexNet or PGGNet, we do have some other architectures as well, like LayNet. I haven't discussed it, but we do have such architectures where we have used either either 3x3 filter or 5x5 filter or 7x7 filter with respect to each layer, and we obtained some output unit. And in detail for the past two architectures, I've already explained how do we compute the number of parameters required, okay, with respect to each unit, correct? And what is the output image? How do I compute the output image, given input image and kernel size? As well as we have also computed how to compute total number of parameters with respect to each layer which are required, okay, given input image. Again, the other parameter, other values, variable values, right? So again, to compute the parameters, we have discussed in detail that to compute parameter, I need filter size, number of filters that I am going to apply, as well as the input size, right? So if this information is provided, then I can say I will be able to compute the number of parameters which are required for each unit or each layer. Okay, in the past few architectures, we have either applied 1x1, 3x3, 5x5, or 7x7. Okay, but in this GoogleNet architecture, we are going to apply all such uh, type of filters on the same input image. Okay, and after that, we are going to like stack output of all these individual units will be stacked together to form one output unit. This is the first and foremost difference between the previous architectures and this architecture, right? So the difference is there we do apply one filter, okay, n number of filters, but one type of you can say the size of the kernel will remain same. Either I apply 3x3, n number of 3x3 on the input, and I get the output. And again, I can take some other 3x3 or 5x5 size filter, and again I will get some other output image. But in sequence we do apply, okay, whereas in this we are applying parallelly. That means I'm going to take the input, I will apply the convolution 1x1. Similar in the previous, let me take to this figure. For the given input image, I will apply 1x1. In parallel to that, I will apply 3x3. Again, on the same input image, I will apply 5x5. On the same input image, I will apply 3x3. Like this, all the operations are done in parallel. And again, the output generated by these convolutions will be stacked with each other to form single output unit. Okay. This is the difference. There we do apply filtering layer by layer, right? Here in each layer, this itself is considered as one module, and in this module we are applying all such different filters we are filter size we are applying. That means we are performing convolution operation with varying the filter size in parallel. Okay, that is the difference. Now let us come back to the Inception module with some concept called as dimensionality reduction. Okay. So as such, if I use direct 1x1, 3x3, 5x5 or some max pooling operation, then dimensionality of the output will become very high. So I don't want to take, or I don't want to use such a high dimensional operations or such a high dimension output I don't want to get. So for that sake, I just want to reduce the dimensionality as well. Okay, definitely I want to apply these filters, but these varying size of filters, but with reduction of the dimensionality, just to lower down number of resources that require. Okay, I don't want to use higher dimensionality operations. For that sake, how do we use, or how do I make sure that I am going to build Inception module with dimensionality reduction concept? We can achieve this with the help of something known as 1x1 convolutions. Okay, so for the given input image, I will take 1x1 convolution and I will get, suppose, output O1. Next, just as described in the previous case, for the given input image, directly I will not use 3x3 convolutions. Instead, I will be using 1x1 convolution first, and later on I will be using 3x3 convolutions. Similarly, before using 5x5 convolution, before applying 5x5 convolution on the given input image, sorry, I will be applying 1x1 convolutions, and later I will be performing 5x5. Whatever result that this 1x1 will generate, I will apply 5x5 on that, on top of that. In a similar way, I will take max pooling of suppose try 3x3. On top of whatever result this max pooling is generating, on top of that, I will use 1x1 convolution operation. Okay, like this, I will be getting some outputs. Output units 1, output units this, output units 3, and output unit 4. So all 1, 2, 3, 4 will be stacked on each other. Fine. So let us move to the next one, that is Inception module. We have already seen what does this Inception module comprises of, but what is the importance we will discuss. Fine. Till now, we have either applied, till now means till this architecture, we have either applied this, or max pooling operation. This I have already discussed in previous slides. Okay. Now we do compute 1x1, 3x3, and 5x5 convolutions for the given input image. Why do I prefer to use such variant filters? Okay, why not only to go sequential? Why we are trying to achieve the parallel computations? Okay, with 1x1 filter, when I apply on the given input image, I may not be I may be using a very fine feature details as well. That means in my feature map, I am going to retain very fine details. Okay, and if I use suppose 5x5 filters, then I will be using, you yourself can imagine using this 5x5 on any input image such as suppose 56x56x3. So I will, if I convolve with 5x5x3, then on with 5x5 pixel, okay, I will put this 5x5 kernel over the 5x5 of my input image, and later on I will apply that multiplication will be done, and later on the summation will be done, and that value will be taken carried forward. So when I am applying on 5x5, that means all those neighborhood values 5x5 25 pixels are responsible to for giving me the output. Okay, so here it provides the fine feature details with respect to 1x1 and bigger details with respect to 5x5 convolutions. That is why we are interested to apply smaller kernels as well as some bigger kernels. Correct? That is the use of using parallel computations, keeping variants of kernel sizes. Now, before moving ahead, let us try to understand what we mean by how do we achieve this applying various kernels on the given input image. Okay, so computing different kernels 1 cross 1, 3 cross 3, 5 cross 5 for the given input image, it may result in different output images. Okay, output. Okay. So when we apply different kernels like 1 cross 1, when I apply on a given input image, it may result in some output dimension. Okay. Similarly, if I apply 3 cross 3, it may result some. Similarly, if I apply 3 cross 3, it will result in some other output dimension. Okay, and if I apply the 5 cross 5, it may result in some other output dimension. That means when I apply different kernel sizes on the same input image, that means height, width and depth remain same. For when I apply that on different or varying kernel sizes, it results in different output volumes. Getting it? So how do I apply, then how do I make sure that I'm going to concatenate the output of this, output of this, output of this, and output of this. To concatenate height and width of the output of this resultant output, of this resultant output, and of this resultant output should remain same. Then only I can make sure that, or I will make sure that my output units are like I can stack on one on another, right? But here we are going to get different output volumes, right? So how do I achieve, or first thing is when I want to achieve, or when I want to apply all type of convolutions, varying convolution sizes on the given input image, then I need to make sure that this will remain same, right? This particular output units output volume should remain same. So how do I achieve that? By using appropriate padding in different kernels, we can attain the same outputs, right? Again, in terms of height and width I am talking about. Let us take an example and try to understand. Suppose if I take 5 cross 5 cross 3. Okay, this is my input. On this given input, I take the kernel size 1 cross 1 cross 3. Okay, and when I convolve it, I'm going to get 5 cross 5 as my output image. Correct. Similarly, on this given input image, when I apply 3 cross 3, then I'm going to get the output as 3 cross 3. Okay, again, use the same formula that we discussed in the last class with stride as 1 and padding as 0, then you will get this. See, in a similar way, 5 cross 5 cross 3 on this input. See, for all these three operation, I'm taking same input volume. Okay, 5 cross 5 cross 3, when I apply the convolution of size, kernel size 5 cross 5 cross 3, then I'm going to get the output as 1 cross 1. So here you can check, one is resulting me 5 cross 5, the other one is resulting me 3 cross 3, and the third one is resulting me the 1 cross 1 output, right? Output image. So how do I perform the concatenation? Okay, concatenation can be done only if their size matches, right? So to achieve this, as I discussed in the second paragraph, we need to use appropriate padding. So how do I achieve that? So for example, 5 cross 5 cross 3, when I apply 1 cross 1 cross 3, I get 5 cross 5. Similarly, for the given input image, 5 cross 5 cross 3, when I use 3 cross 3 as my filter size, 3 cross 3 cross 3, and with padding value as 1, I am going to get 5 cross 5. Okay. And in a similar way, on this given input image, when I apply the filter 5 cross 5 with padding as 2, I'm going to get 5 cross 5. Like this, I'm in this example, when we use P as 0 here, P as 1 here, P as 2 here. So with different appropriate P values, I'm going to get the same output units. Okay, now I can stack all these output units together, right? With this information, let us move to the next part. Okay, till now it should be clear, like given input image with appropriate padding, I'm going to get the output image same, even though we are varying different kernels, right? So let us move to the next one, that is importance of this 1 cross 1 convolution. Why we are specifying this? Okay, this is clear, but let us move to this. Why I am going to use 1 cross 1 before 3 cross 3, 1 cross 1 before this. Okay, why? What is the importance of using 1 cross 1 before applying 3 cross 3 or 5 cross 5? Even after max pooling, why do I use this 1 cross 1 convolutions? Let us see that. Let's take an example with input image 14 cross 14 and depth here is 480. When I apply the filtering on this given input image of 5 cross 5, okay, and how many filters I'm going to apply on this particular input 5 cross 5 cross 480. I'm going to, let's take just an example, 48 different kernels I'm going to use. When I use 48 different kernels, I know my depth will remain 48, will change to 48 because I'm applying because I'm going to apply 48 kernels or 48 different operations, kernel operations on this particular given input. Hence, my output depth will be 48. Whereas height and width will remain same 14 and 14 because we know that we are applying 5 cross 5. Okay, and when I keep the padding value as same in my Python, when we use implementation, and if I keep appropriate padding, then it is very much clear that I may be able to achieve the same dimension, that is height and width as well. So here height and width 14 cross 14, I am going to get the 14 cross 14 only. Correct? So with how much padding you must be able to compute. By this time you must be able to compute. By this time you must be able to compute how much should be the p value, so that I must be able to retain this height and width in the output image, same as my input image. Okay. Now let us see. Suppose we have generated this 14 cross 14 cross 48 as my output volume. Okay. So once we generate output volume of 14 cross 14 cross 48 for each generated pixel value, okay, we need to perform how many computations or how many operations we need to perform to get just simple single output cell in my output volume. I need to have for this, I need for each element, if I need to compute for each individual element of 14 cross 14 cross 48, I need at least these many operations, 5 cross 5 cross 480. And you all must very well understand that if we use 14 for this particular output volume 14 cross 14 cross 48, for single individual element I need these many operations. For all, if I need to compute for all individual pixels, I must be multiplying this 14 cross 14 cross 48 times this. Correct? So total number of operations, different operations that require to compute all the pixel element values, then I need to have these many operations. That is 14 cross 14 cross 48 multiplied by 5 cross 5 cross 480, and it results me 112.9 million operations. Correct? Now, let us take, or let us try to introduce 1 cross 1 operation. Okay, let us try to use 1 cross 1 filter just before using 5 cross 5. Same I am going to apply. Here also we have used on this particular input image, I have used 5 cross 5 48, and it resulted 14 cross 14 cross 48. Fine. For the same given input image, instead of directly applying on 5 cross 5 48, because when I applied directly 5 cross 5 cross 48, so it resulted 5 cross 5 filter on with 48 number of filters, it resulted in so many operations, okay, which require. So just to, as I can see, when I apply 5 cross 5 cross 480 on this input image, 48 numbers if I apply, okay, only for this particular one filter, I'm going to get, I need to perform these many operations, which is very high. So how do I reduce it? I can reduce it by using this 1 cross 1 convolutions. Let us see. Let us try to compute how many operations we require for this as well as for this. And later on, if the sum comes out to be less than this, then we can say that we can introduce this 1 cross 1 filter, right? Or I can apply 1 cross 1 before applying 5 cross 5 filters, right? So let us see. Total number of operations I need to do it together for 1 cross 1 as well as for 5 cross 5. Correct? So here what we need to do is we need to first check for each resultant intermediate output unit. For this output unit, I need to check for each individual pixel values, or the resultant output that I need for each individual element. Okay, I need to compute for that. Similarly, I need to compute for this particular output. Okay, so when we take for this 14 cross 14 cross 16, we need each element, it needs how many? It needs at least, it needs actually 1 cross 1 cross 480. Okay, and for this it needs 14 cross 14 cross 480 for 48 for this output. Each element in this output we need 5 cross 5 cross, how many we should get? At least 16, right? So let us compute it. 14 cross 14 cross 16, this for this each individual, for this particular output we need 1 cross 1 cross 480, right? Plus 14 cross 14 cross 48, we need 5 cross 5 cross 16. We need 5 cross 5 cross, and depth here is 16, right? So you must understand, we are going to get the we are going to compute the aggregation over the full depth. Hence, we are taking 5 cross 5 cross 16 here. Remember, we always take the kernel depth as same as the input depth. Why we take kernel depth as same as the input depth? Here, kernel depth of this will be same as this input depth, that is 480. Why do I choose that? Because first, for the first depth, I will compute convolution, and again for the second depth, again I will compute convolution for the third and for the fourth, and later on I will take the sum over the entire depth, and I will generate one single pixel, right? For that sake only, I always say I do take filter size, depth of the filter same as input depth. Okay, because 5 cross 5, suppose I do take, let us take an example. Suppose I have 2 cross 2 filter. Okay, and I have the depth. This is the filter size and this is the depth. Okay, now what I have is, I have suppose my input. I have my input. Input again, depth here is 2. Fine. So what I will do is, I will take the depth here, means I do have two set of feature maps, right? I have, this is first feature map of my input, this is second feature map of input. For that sake only I do say it as in depth as 2. Let me call this one as 1 and this one as 2. So why I've taken this 2? Because I take 2 cross 2 on this. I will keep 2 cross 2 on this input image. Let me add the slide. This is my first feature map and this is my second feature map of my input volume. This is my input volume. And I do take, suppose I have taken 2 cross 2 filter. Okay. And here I will also be taking 2 filters. Why I should be taking 2 filters? This is the first filter that I'm going to take. This is the second filter that I'm going to take. Why should I take this? Because this first kernel I will keep on this input image. I will perform convolution and I will generate some output. Okay, I will, that means I will first perform this on this 2 cross 2 input. I will keep this 2 cross 2 kernel. I will perform some convolution and first pixel will be generated. Whatever value, because I have not placed any values. So whatever values, some random value, I will perform this F11 into this I11 and F12 into I12, F13 into I13, F14 into I14. That means I'm multiplying each individual corresponding pixels of image and the kernel, and later on the result will be added after this F11 into I11 plus F12 into I12 plus F13 into I13 plus F14 into I14. Whatever result that this operation, okay, multiplication of filter value of image value and later on take that summation and it may generate some pixel. Okay, I will keep over here and I will move my filter to the next element. Next element in the sense I will stride over the input next 2 cross 2 depending on stride rate. Okay, if stride rate is 2, then I will leave 2 columns and I will move to the third and fourth of my third column and fourth column of my input image. Fine, like this I will be generating. This is the resultant of applying the first kernel on the first feature map of my input. I will take second kernel and I will apply the, I will again perform that multiplication operation and I will add to this. Right. So like this, I will perform individual kernel map will be convolved over the individual feature map and their average values, summation value will be taken as my resultant pixel value. This you all must understand. That is why I always say that we must take, that is why we always prefer to take the kernel depth as same as my input depth, right? So now for this we need how many? We need 14 cross 14 cross 16 into 1 cross 1 cross 480, plus we also need 14 cross 14 cross 480 into 5 cross 5 cross 16. So it results me 5.3 million number of operations, which is much lesser than using this 112.9. Why it has reduced the total number of operation? Because of this, because we have introduced one intermediate operation, that is using one cross one convolutions. Okay, it has reduced. Okay, why it has reduced the total number of operation? Please try to understand. Here it has reduced because earlier, sorry, okay, there is some issue, right? Okay, now try to understand why this 5.3 million total number of operation, when I introduce one cross one, it has reduced to 5.3 from 112.9. Why it has reduced? We must understand this. It has reduced because we have introduced one cross one convolutions. Okay. Again, try to understand. Here also input image remains same, as well as output image will also remained same, but only difference, and also here also we have applied 5 cross 5 filter, right? Here also we have applied 5 cross 5 filter. Only change that we have done is we have introduced something known as 1 cross 1 convolutions. Okay, why it has happened? Because see here, the depth here was 480. Okay, so here the depth was reduced when I apply 1 cross 1 filter convolutions on this 480 depth, that is on this particular input. When I apply 1 cross 1 cross 480, because I've taken 16 number of filters, so it has reduced the depth of the intermediate input image, right? So you all must understand, because we have reduced that earlier, the operation 5 cross 5 we are applying on this depth 480. Here now 5 cross 5 will be applied on this depth, that is 16. Hence this reduced number of total number of operations. Okay, that is the importance of introducing 1 cross 1 convolutions in case of the GoogleNet architectures. Okay, just taken an example, like just not to use, not only to use 5 cross 5. If you want to use 3 cross 3 also, you can take any example input volume and try to compute the output volume, and try to compute number of operations which required for each to get each individual pixels on 3 cross 3, on 5 cross 5, or any other, on any higher number of kernel size. Okay, when you apply directly on the given input image, when you apply directly 5 cross 5 or any other kernel size operation, okay, total number of operations will be high as compared to when you introduce some 1 cross 1 convolutions. Okay, you can try at home, like change values. Instead of 5 cross 5, you try to change 3 cross 3, 7 cross 7, and you try to get the total number of operations. And definitely when you introduce 1 cross 1 convolutions, it should reduce the number of operations, provided the number of filters on this intermediate operation should be less. If it is greater than 480, then there is no use of using this 1 cross 1 convolution. Okay, let us move to the next one. So the major change in GoogleNet was not to use, not to have sequential operations. Okay, it does have sequential operations like convolution pooling, like this. It has some convolution and pooling layers in the initial stages of the architecture, whereas later on it has introduced 9 different inception units. Okay, that is the first change. That means instead of only using convolution and pooling layer one after the other, it has introduced set of convolution pooling layers in parallel. It has applied, right? So that is nothing but Inception unit. So it has introduced Inception unit. Apart from Inception unit, there is also advantage of using 1x1, thereby reducing
You are not audible.
Am I audible?
Yes, ma'am.
Yes, ma'am, you are audible.
Let me know where it got disconnected. I
Okay,
will
ma'am.
share. I will share the PPT
Okay,
again.
ma'am.
On which slide it got disconnected?
Ma'am, it was this slide only.
Okay, okay, fine. So let's continue. So instead of fully connected layer, having fully connected layer, it has been into average pooling concept has been introduced. So in this, without having, like, if I need to have fully connected layer, first of all, this is the out. This is the result of last inception module. Okay, so if I need to have dense connections further, then we all know we need to flatten this out. Okay, so how do I flatten? I need to convert this 7 cross 7 cross 1024 into single vector, 1D vector. Okay, so how many cells it will have? It will comprise, if I need to have if I need to flatten this, then it will have around 7 cross 7 cross 1024. That means so many like connections that I need to have, right? That means 7 cross 7 cross 1024. But here, what it has done in this, it has been introduced the global average pooling. What is the meaning of global average pooling? Is each 7 cross 7, what it will do is it will take the average of that and it will have the connection with next, that is individual 1024. Fine. So by how much it has reduced the competitions? Okay. Suppose earlier we were having 7 cross 7 cross 1024 as my flattening layer. But now when I use average pooling, now I will be having 1024. Correct? So this is how it has changed the or it has reduced the number of competitions which are required. It has reduced at least by 49%, right? Almost half. So this is the overall architecture of the GoogleNet, right? So like initially this is the input and this is the output that it is going to get. So from in this input, I know it's very I've shrink the image because it's not coming on the single slide. So I will read it out for you. This is the input image. Later on we will have convolution, pooling, convolution, and so on. And this is where we are having first inception module. This is the first inception module that we are going to have. After this first inception module, that means after this, we will be having second inception module. After this, we will be having next inception module and so on. These are the next inception modules, right? And we also have some auxiliary modules. Two auxiliary modules have also been introduced. So here auxiliary modules are being introduced to get the intermediate output. Using softmax, they are going to get the intermediate outputs. Okay, just to check the representations of intermediate layers. Otherwise, we do have so many inception modules, first, second, third, and so on, till 9 inception modules we do have. So let us discuss one inception module, how it looks like. We do have input. Suppose we do have 28 cross 28 cross 192 as my first inception module. Okay. When we apply 64 different kernels and when I apply 1 cross 1 convolution on this particular input, then it will result me 28 cross 28 cross 64. Okay, this is what we have been discussing since the CNN architecture. Okay, when we apply 1 cross 1 on this, again use the same formula, you should be able to get this. Okay, next, when we apply 96 kernels of 1 cross 1 on the same input image, okay, I'm going to have 28 cross 28 cross 96 as our output. Okay, on this output, I will be using 3 cross 3 filter. How many filters I will be using? I will be using 128 filters. Suppose I will be using 128 filters. Then what it will result? It will result me 28 cross 28 cross 128. Right? In a similar way, I will be using, I have used 1 cross 1 filter. I have used 3 cross 3. Before that, I have used 1 cross 1 and 3 cross 3. Next, I will be using 1 cross 1 and 5 cross 1, 5 cross 5 filters. I will take 16 number of filters. I will use 1 cross 1 on this input image. Okay, see, see here, this operation, and this operation, and the next operation. All 4 operations we are doing on the same input image. That is 28 cross 28 cross 192. Okay, when we apply this, this is the intermediate output that it will generate, output volume that it will generate when we apply 1 cross 1 on 16 number of filters. It generates 28 cross 28 cross 16. Once we get this, I want to apply 5 cross 5 filters. Okay, 5 cross 5 filter. How many? 32 number of filters I want to apply on this intermediate output to get the final output. Okay, that is 28. What is the output volume that I will get? I will get 28 cross 28 cross 32. Okay, once we get this, this is the output that I get when I apply 1 cross 1 filter of 16 1 cross 1 filter and then 5 cross 5 filter. Okay, 32 5 cross 5 filter, we will be getting 28 cross 28 cross 32. Afterwards, we will be applying max pool operation. First, I will apply max pool on this 28 cross 28 cross 192. I will be applying max pooling. It will generate 26 cross 26 cross 192. And later on, what I will be applying, I have not written here. I will be applying 32 numbers of 1 cross 1 filter. Okay, when I use 32 number of filters, with each 1 cross 1, I am going to get 28 cross 28 cross 32 as my output volume. So now I do have generated 4 different output volumes. One, when I simply apply 1 cross 1 on the input. One, this I applied 1 cross 1 and on top of that 3 cross 3. This is the result when I apply 1 cross 1 and on top of that I apply 5 cross 5. And this is the result when I apply 3 cross 3 max pooling and on top of that I will apply 32 numbers of 1 cross 1 filter. So it results me 28 cross 28 64, 28 cross 28 into 128. Similarly, 28 cross 28 into 32 plus 28 cross 28 into 32. So what I need to do is I will be stacking all these output units on one on the other so that it should generate a single output volume. Okay. When I stack all of them, it will generate 28 cross 28 cross 256 as the output of the first Inception module. Okay, like this we will be having next Inception module. Again, in next Inception module, we will be using 1 cross 1 some filters. We will be applying some number of filters of 1 cross 1, some number of filter of 1 cross 1 and 3 cross 3, and some number of filters 1 cross 1 and 5 cross 5, and max pooling, and then followed by 1 cross 1 convolutions, so that it will generate the output volume. And this output volume will be input for the next Inception module. Okay. So with this, I have completed the GoogleNet architecture, details of the GoogleNet architecture. So this is the reference paper. Okay, you can refer this paper as well, going deeper with convolutions. I have only computed, just for illustration, I have only computed the output volume resultant of first inception module. Like this, we do have 8 different inception modules which are available. You can compute for each individual input, like for each individual inception module, you can compute the output volume that it will generate. Okay, as well as you can even try for computing number of parameters in each layer. Because I've already explained the formula I've given in the previous sessions, you can use the same formula and you can compute how do I generate the output volume with respect to each inception module. Okay, definitely do refer this particular paper for detailed architecture of GoogleNet. Okay, these are some other references that I've referred for today's session. I'm done with today's session. If any doubts, do let me know. Any queries? So we have done three different architectures: AlexNet, VGGNet, and GoogleNet. So in coming class, that is next session, we will see the practical implementation of these architectures with the help of transfer learning concept. Okay. Sakshi,
Yes, ma'am.
I'm done with today's session.
Okay, ma'am.
If there are no queries, we can close this session.
Okay. So is there anyone having any doubt?
No, ma'am.
So, ma'am, I think we can end the session now.
Okay, thank you so much.
Thank you so much, ma'am. So I've pasted the attendance link into your chat window. So do complete your attendance by within next 10 minutes. Otherwise, the link will be disabled. Thank you so much, everyone.